Okay, so we start now. So it's my pleasure today to introduce you to engineer Gian Maria Marconi. And he's a PhD student joined between here and the Italian Institute of Technology, and today he's going to talk to us about structured machine learning.
Thank you, Luigi, for the nice introduction. And as many of you may know, I deal with machine learning, essentially. In my case, structured machine learning. So the idea is when the output is not the usual stuff you can see on traditional algorithms, but some more exotic kind of output. So today I will tell you about my last work that I did jointly with Alessandro Rudi and Carlo Ciliberto, two former postdocs here, and Lorenzo Rosasco. So let's start from the beginning, which is already always a good point to start from. So for those of you who are not familiar with machine learning, the basic idea of machine learning is that we are given a data set of input-output couples. And the idea is that we want to learn a function that goes from a linear space to the real line that can, in a certain sense, learn and code the relation between the input and the output and can generalize for future inputs. So every time we get a new input in the future, we can do a prediction of what is the best associated output Y. So this is a classic problem of regression. And it's very similar when we do classification. Instead of predicting just a real value for the output, we want to classify it either in class 1 or class 2. But this is entirely similar to previous problem because essentially what we are doing is that we are learning a separating function that partition our spaces in two classes, so we can either assign one of the two main classes to the new point incoming. So this is what machine learning traditionally does, but there is, let's say, a problem. I mean, not a real problem, but this is a bit constraining because actually in these two examples, the output is always the real line. So it's a very simple output space. So the question becomes, what do we do when the output space is something more complex? As an example, take a nonlinear space, a curved space, a space made by time series, a space of graphs, or a graph itself, where each node is an element of the space. So this is essentially what structured machine learning tries to study. And today I will talk to you about, in particular, one of these spaces, which is curved spaces. More specifically, it's differentiable manifolds. So today we'll see how to do prediction when our output space is a differential manifold. So imagine a linear space, which is not linear, essentially. So we'll see now some examples. So this work is titled Manifold Structure Prediction. So this is the problem. We want to learn a function that goes from a linear space, so the input is still a vector, to a manifold. So our outputs lie on a specific manifold. So what is a manifold? Where, for those of you who are not familiar with the concept of manifold, like me, a manifold essentially is, you can see it as a curved space that locally is isomorphic to a linear space, which means that if you take a point and you zoom close enough to this point, it's like you're seeing a linear space. The classic example of this is a sphere. When we are on Earth, we see everything as roughly flat, but if we zoom out, we realize that this is not true. Unless you're a flat earther, then you also think it's flat. But it's another story. So the idea is that essentially, if you're locally, you have a structure which is very similar to a linear space, but globally, this is not true. And the problem might become something like, I give a vector, and then I want you to predict a point on the sphere. Well, this is just the simple example I can give you about manifold, but there are many more different manifolds that can be much more complex, like, for example, think about the set of positive definite matrices. This is indeed a manifold. So we have to introduce some tools before going into the algorithm, and these tools are essentially functions that deal with manifolds. So as I told you, the manifold, it can be thought of as a curved space. So the first tool we need to introduce is the tangent space. The idea is that, think always of a sphere now. I take a point, the tangent space is the plane tangent to that point. What is nice about this tangent space is that indeed is a subspace which is linear. So what we can do is that we can impose a structure vector, a vector structure, sorry. And so we can do all our weird stuff that we are used to with linear algebra. So this is very important because in general, points on manifolds do not have a vector structure. So usually if I tell you, okay, I give you 2 points in a sphere, I want you to sum them, you're not supposed to know how to do it unless you put a structure vector on these points. So this is the first thing, tangent space. And this is indeed a nice approximation of a linear space centered on a point of interest. Secondly, then, we introduced the exponential map. So we saw that we can do now a lot of linear stuff inside the tangent space. Now the problem is, when we move inside the tangent space, we are not anymore the manifold, because this is a local approximation around this point. So what does the exponential map? Well, the task of the exponential map is to map each vector in this tangent space to a point on the manifold in a way that is compliant with the geometry of the manifold. So I don't want to go into detail about this, but the idea is that you can do your stuff here with vectors, and then you reproject them back onto the manifold, where this projection is aware of the geometry of the vector. So depending on the curvature, this projection will change. And finally, we have geodesic. So as I told you, we have no vector structure on a manifold. So it's not obvious how to compute, for example, distances between 2 points. Well, the idea is that a geodesic is exactly this. I give you 2 points on a manifold. The geodesic is the curve of minimum length that conjunges, that pass between these 2 points. Because actually you can have infinite curves, obviously. But so the geodesic is just the generalization of a straight line on a manifold. So these are the 3 tools we need now to explain the algorithm. Remember that the problem is, I'm given some points, which are vectors, and want to predict a point on a manifold. So the approach is the following. It takes full hands from structure prediction. So we take an algorithm that is using structure prediction for very generic tasks. In a certain sense, let's say we specialize and we see how to compute it in the case of manifold prediction. So this is the estimator. So we are given an x and we predict a y. Let's have a look at this estimator, this function. First of all, we can notice that this depends on 2 functions. This is essentially a set of weights. This is a function that, given an x, computes some scalar weights. And this is a loss function, which measures how much 2 points in the manifold differ, or how much they're similar, if you prefer to say. And this depends on the problem, obviously. Then, now, what is nice about this estimator is that this loss satisfies some mathematical condition. Then this estimator is consistent. This is nothing to be scared of. This is just a linear product on a reproducing kernel Hilbert space. And this is a linear operator which does not need to be symmetric. So this is nice because this loss doesn't need to be symmetric. So what's important about this estimator is that using it can be split in 2 steps. The first step is training, which is using DEX to compute the coefficient of weights given the alpha function. And the second step is prediction, which, given this linear combination of losses, is to find the y that minimizes this linear combination. So we'll see now how to do this. First step actually is quite easy because it's akin to solving a kernel problem. This is for those of you who are familiar with kernels, it is very similar to solving a kernel bridge regression. So the main problem here is just inverting maybe big matrix, but that's it. Once you have done it, you obtain a coefficient, and this, you obtain a vector of coefficients. These coefficients are the ones you need to plug in here. So you also have to feed it a kernel, but usually standard Gaussian kernel is good enough. The second part is a little bit more involved because it's not obvious how to minimize this. Also, what is nice about this is that this can be done preemptively once we have the training set. Then, once we want to do a prediction, we start and try to minimize this expression. So this is done, say, offline. So let's go to the prediction step, finding the minimizing y. So here the problem is that this is, let's say, a bit of a monster in terms of optimization because the y needs to belong to the manifold. So what we do is that we go and select what is the most similar thing to what we know in a linear space, which is Riemannian gradient descent. This is the equivalent in a Riemannian space, so in a curved space, of the gradient descent. Now, let's go over this a bit. This is very similar to the standard gradient descent. We have two main differences. The first is the gradient. Now, this is not anymore a normal gradient. This is a Riemannian gradient, so it's a gradient computed complying with the geometry of the manifold. So we need some quantities about the manifold. Usually this can be done. There are a lot of books about this. It's not that hard. The second part now is the fact that there is no more subtraction, and it is substituted by the exponential math. Why this is this way? Well, the idea is that we compute the Riemannian gradient on the tangent space of the point where we are. So we have now a vector here, and this is in some way the step we are performing with the gradient descent. Now what we do is that, since we cannot now subtract this point from this point, what we do is that we reproject this vector back onto the manifold, and this is done by the exponential map. So in a sense, we, at each iteration, take the tangent space, do a step with the gradient, and then reproject back on the manifold and repeat until we converge. This is essentially Riemannian gradient descent. And as you may know, there is, let's say, a bit of a difference with respect to standard machine learning algorithm, because usually when I give you a machine learning algorithm, what you do is that you pre-compute it by learning from the training set, and then you just, when you want to do a prediction, you just instantiate it, typically with, you feed it to your neural network, you do a linear product if you are a kernel machine, and so on. Instead, here, every time we want to do a prediction, we have to solve a minimization problem. So this is computational on another level, but also the task is on another level. So now let's go over some results about this algorithm. First of all, there is a theoretical result. So the hypothesis is that for the estimator I showed you, if the loss satisfies this property, then the estimator is consistent and we have finite sample bounds. Now, in our work, we proved that for square geodesic, actually for a wider class of functions, these functions are all self, which means that all satisfy this condition, and thus our structure estimator is consistent and has bounds for almost any kind of Riemannian differentiable manifold you can think of. So this is nice. We like when our estimator is consistent. It gives us some kind of proof of some kind of bounds, some kind of confidence on what we are doing. Now let's go over some experiments. So this is done on a synthetic dataset. Let's take now the set of positive definite matrices, which are essentially matrices which eigenvalues are positive. What you see here is the geodesic of on this manifold. So the main idea is that we are gonna go back. So let's go back to this, to the estimator, and we are gonna use each time as a loss the square geodesic. So this is actually this is already the square geodesic. This is not too scary because this is a Frobenius norm. This is these are usually two positive definite matrices. So this is always symmetric and positive definite. And the logarithm is defined as the matrix whose eigenvalues are the logarithm of the eigenvalues of this matrix. So nothing really complicated. So what we do here is that we take as an input, as the x's, a random positive definite matrix. We vectorize it, so now it's a vector, a very long vector indeed. And we take as an output for this x, the inverse of this matrix, of the original matrix. This is our training set. So what we are trying to do is get a function that, given a vectorized positive definite matrix, tries to learn the inverse of said matrix. And actually here, well, we chose in particular some matrices where the eigenvalues were non-constant. I mean, we had something that was like exponentially decaying in the eigenvalues. So let's have a look. We compared our method with the standard kernel regularized least squares. And we have the squared loss and the squared geodesic, so this distance, depending on the number of dimensions of the space, so the dimension of the original matrix. So if we look at the square loss, we can see that both approaches are not so good actually, because with the square loss, if we just take the identity matrix, we get a loss of 1. So we are not so far from this loss. So we are not very good at predicting entry-wise the inverse matrix. But if we look at the square geodesic, which mostly looks at the eigenvalues of the matrix, we can see that our method greatly outperforms the linear one. This means that while we are not very good at predicting entry-wise elements in the matrix, we are decent at predicting the eigenvalues of the inverse matrix. Now, we'll go over a more practical application. So, this is a fingerprint. The idea is that when I'm given a fingerprint, each pixel in the fingerprint can be characterized by a direction, by an orientation. Also, we should all thank Damiano for the colors on this picture. Thank you, Damiano. And very well done indeed. So every time we get a pixel, we also have an orientation, which is the orientation of the fingerprint at that point. You can see that this is somewhat smoothly varying with respect to the orientation of the fingerprint. So what we want to do is that, given a pixel, we want to predict the orientation of the fingerprint at that pixel. The idea is that we are given just a few points from the original image, maybe because we are missing the remaining points, maybe because the remaining points are too corrupted by noise, so we cannot use them. So the problem now is the input data is a point in R2, and the output data is a point on the most simple sphere, the most simple manifold you can think of, the circle, the one-dimensional circle. So now we want to try to solve this problem. So let's see the results. So in this case, in the case of the sphere, this is the square geodesic, where these are 2 points on the sphere seen as belonging to a. So suppose I give you an n-dimensional sphere. These 2 vectors are vectors of n+1 linear space. So you can always see a sphere embedded in an n+1 dimensional linear space. So if I give you a circle, you can see a circle as part of R2. If I give you a sphere, you can see a sphere as part of R3, right? Right. So first of all, we have here in the table the average error in degrees over roughly, I think, 52 different fingerprints, where we compare what we obtained with kernel regularized least squares, a state-of-the-art method for manifold-to-manifold regression, and our method. You can see that our method outperforms both previous method and has lower variance. Also here you have a qualitative evaluation of what our method actually predicts. So this is the original image from which we sampled only 1 pixel out of 10. This is what the kernel ridge regression predicts, and this is what the structured estimator predicts. You can see that this, I would also prefer this to the original image. I don't know you, but this seems nicer, smoother. Also, well, this is because the original image was corrupted by noise, because actually these were real images coming from, I think, a database took in Bologna some years ago. So what is nice is that our method in general, when predicts a point, we're always sure that the predicted point belongs to the manifold, because we go back a bit. The minimization step here always returns a point that belongs to the manifold, because every step ends with reprojecting back from the tangent space to the manifold. And usually, well, almost never this is true if we use a method that is not aware of the geometry of the outer space, like a kernel regression. So indeed, for example, if we look at this experiment, what we actually did is that we had to, when we did the prediction with KRLS, we had to do a spectral decomposition of the matrix, and then we had to project the matrix onto the positive manifold by setting the negative eigenvalues to a small epsilon. Also here, every time we got a prediction with the ridge regression, the prediction could really be into the real line, so we had to clip it to be into the interval 0 to pi. Well, this never happens if we use this kind of estimator. Also, this estimator while it does approximately tries to predict a value that belongs to the manifold, actually it usually works on an ambient space which is bigger. So if we were to work on the circle, this method is actually working on the R2 space and try to impose the predicted value to be onto the sphere by some kind of regularization. So let's go over some future application from here. So we have seen that right now we are quite comfortable doing predictions in manifolds. So let's introduce now a new manifold. It's essentially a hyperbolic space. The idea is that I give you, let's take now the circle in R2, the full circle this time, okay, not just the circumference. Well, the idea is that this is the geodesic between 2 points. As 2 points get closer to the edge, their distance exponentially goes to infinity. So why? We are not interested in why, but the nice thing about this kind of space, which is a hyperbolic space, is that it can be shown that it's a very natural way to embed trees or graphs. Why? Well, suppose I give you a tree and I tell you that at each node you have a fan out, so a number of child which is constant like n. Now I tell you to go down this tree, and so at each level you can see that the number of child, the total number of child you have increases exponentially with respect to the level. And this is very similar here because as we now take a subcircle here with a fixed radius, make the radius grow, the length of this the circumference grows exponentially. So this is it. Hyperbolic space, very good for embedding trees, also graphs that do not have too many cycles. So what do we want to do? Well, recently in the literature we have seen some nice work about hyperbolic embeddings, which essentially boils down to taking a graph and embedding it in a hyperbolic space. You can see an example here, I don't know if it's clear. For example, this should be the wordnet, mammals, the mammal sub-branch of wordnet, embedded into this space. You can see that here, this close to the center, you have mammal, and you get closer to the edge, then you get, let's say, big subnodes like we have ungulate, ungulati, and carnivores, carnivori, and so on. And then as you go closer to the edge, then you get stuff like tigers, cats, squirrels, and so on. This stuff seems to work very well. Well, the idea is, when we compute these embeddings, what we do is that we take essentially a dataset which is composed only of the labels. So suppose I give you a standard machine learning dataset, which is features and labels. Remove for a second the features, take only the labels, and now you have a function that defines a structure, an ontology on your labels. Given this function, you can compute now the embedding. But the idea is, what do we want to do now? Something more. We want to do actually machine learning. So we want to learn from an input to an output. So now the goal is trying to build an embedding that is aware both of the structure on the labels and on the features. Now, once we have this embedding, so for example, in the embedding, we could have a label by itself, but also as a subnode, an instance of that label. So we could have tiger here, and here we could have a point associated to a picture of a tiger, or to a text describing a tiger. So a feature associated to that label. Then, since this is essentially a manifold, what we want to do is we want to perform predictions on this space. So the idea is that we can now use this estimator, take a new point, so a new feature, so for example, a picture of a tiger, and try to predict its position on the embedding, and see what happens. So that's it for the future work. This is very much work in progress. Like right now in the Odger lab, there is a machine running trying to crunch code about this stuff. And let's go over some conclusions. So in this work, we propose a consistent model for learning manifold-bodied functions. We show how to actually compute this model to perform the minimization for computing the model. And we show some application in synthetic and real data. Some open questions are, we didn't investigate the convergence of the geometrical optimization tool we use. Well, the problem is that the estimator I showed you is essentially a non-convex problem. So actually, for now, we know almost nothing about what we can say, about what any kind of guarantee we can give. Also, are there better minimization methods? Because this is, I mean, we look a bit into this, and the Riemann gradient descent seem to be, let's say, the best one, the most reliable one. But maybe there is something more exciting that we were not aware of. And finally, well, future application, I just introduced them. It's using the hyperbolic embeddings to, let's say, exploit even more the structure that some datasets have on the labels. That's it. Thank you for your attention.
Okay, so Gian Maria, any question from the audience?
Yes, so I was wondering, since you can embed a manifold in a replicance-based bigger dimension, so if you try to do machine learning in this more traditional setting, and you said that maybe you can play with the regularization component of that. Are you able to get the same results by playing just with the regularization, or
so yeah, okay.
It's completely different?
Let's go back. Okay, so in terms of pure results, we have an example right here, because this method is manifold to manifold, but always starts from the working hypothesis that all the manifolds are embedded in a linear space, and it does exactly what you said. So it forces, with the regularization, the outputs to lie on the manifold.
Sorry, which one of the
images? The image is not here because it was too small on the paper. So we didn't put it here because it was too low quality. The middle one. Oh, I missed the reference here. I don't know why it disappeared. I will put it later. If you're interested, I can give it to you later. And well, the first thing about this method is that there are no proof about statistical consistency. And the second problem is that if we do not have a manifold that is immersed in a linear space, there is no clear way to use it. While this method, our method, always works for any kind of manifold as long as we have tangent map, tangent map, exponential map, and the square geodesic.
So you are saying that if you try to embed it in the Euclidean space, there are examples of manifolds where you cannot recover your result by playing with the regularization component.
So we do not have a clear theoretical examples, but I mean, we developed this method and we just stick with it because we knew it had some nice statistical properties. The old method we were aware of, this one, which is the most recent and most studied one, does not have statistical properties, and in this specific example showed a worse performance. But yes, I mean, I think that playing enough with the parameters, I think you could recover some decent results. The question is, how hard is it to do so? How much do you have to fiddle with your hyperparameters to have an algorithm that nicely predicts stuff on your manifold?
The second question was, you take, you assume that the output is on a manifold, but you stick with Euclidean space in the input.
Yes.
What happens, for what reason this asymmetry? What about?
Because, well, because actually because we started from this estimator, which is somewhat of a recent work, it's from 2 years ago, and the derivation of these estimators, it can be done only right now under the hypothesis that the input, it comes from a linear space. That's it. That's more of a technical reason. We didn't investigate yet when the input is also manifold valued. But it could be an interesting possible direction.
delta y, yi. And you said that you can have a transformation v in the middle. You said
A transformation?
You can have a transformation v in the middle.
No, the transformation V is in the loss.
In the loss, okay. You said that you were, I mean, it wasn't symmetric.
Yes. So essentially this tells us that
So
this
it's
loss.
not a kind of distance in the usual sense.
Yeah, it is not. It's a generalization of the distance. It's a non-symmetric loss function essentially. But in all the experiments,
Why like it? I mean, do you have any?
I couldn't find any problem. I mean, it's a degree of freedom you have when you use this, but I didn't find any problem where this was necessary. All the problems I showed you, they were symmetric. Symmetric. I mean, maybe it's not obvious, but it can be shown that it's symmetric using the property of the trace inside the Frobenius norm. And this is symmetric because the inner product is symmetric. Yeah.
So if you go back to the optimization problem, essentially you project it's a form of projected gradient descent. The first question is the projection can be, because you say now this is more expensive because I have to solve a minimization problem using projected gradient descent. Even just the projection could be super expensive.
Yes.
In the projected gradient descent. And then the other thing is, do you have any guarantees of convergence? Because on projected gradient descent, if your actual optimum is outside of your manifold because of noise or whatever is happening, you might end up bouncing back and forth in your projected gradient descent.
So I have some guarantees for some G-squared geodesics, but I mean are the usual rates of non-convex problems, so they suck. They're not interesting. And they depend, you have to do the computation every time depending on the manifold. We don't have a general result for a whole class of manifolds.
But at least you have convergence, for example.
Yeah.
Even if the actual optimum is outside of the manifold.
I don't remember the proof right now, I should check it. I think so, but I should check it. Also, there is a thing that the exponential map is a bijection as long as the step is bounded by some constant that depends on the manifold. I mean, suppose I give you a sphere, you have a tangent plane, you know that at most you can do something that's like the radius of the sphere, otherwise you just go out and everything sucks. If you stay inside the radius of the sphere, then you should be good.
Yeah, but you still can have oscillation.
Yes, indeed, it should be strictly smaller than the radius.
Even if you're sitting smaller than the radius.
It's also if it's inside the sphere.
And imagine you have this sphere, the optimum is here, you start from here, you go like this, you jump here, you go like this, you jump here, you go like this, you jump here, you go like this.
No, because since this is well, actually we use the stochastic version, so this is the eta is decreasing until here.
Then you might not.
Okay, we can discuss this offline.
Questions? Otherwise, we thank Gian Maria again.
Good.